So hello everyone, welcome to the Gate Wallah and good evening everyone, very good evening to all of you. So we will continue our discussion on the fault analysis of the power system. On Monday we started the topic of fault analysis of the power system, and till now we have discussed about the symmetrical fault and the sum of the unsymmetrical fault. So till now we have discussed what is the symmetrical fault and what is the unsymmetrical fault. It has already been discussed how to find out the fault current when the symmetrical fault occurs into the power system, and how to find out the fault current when the line to ground fault occur into the power system. I also gave the idea about the sequence network, how we can draw the positive sequence, negative sequence and the zero sequence network. Now we are discussing about the line to line fault. So yesterday we started the line to line fault. Whenever the two phases are short circuited, it is called the line to line fault. When the line to line fault occur, no zero sequence current is flowing in the power system. Only positive sequence and the negative sequence current is flowing. And I told you, whenever the line to line fault occur, the positive sequence network and the negative sequence network would be connected in parallel with a impedance of ZF if the ZF is there. Now, yesterday I told you how to find out the value of the fault current. We also derived the formula to find out the value of fault current. Today, I will continue our discussion for line to line fault, and after that I will start the double line to ground fault. Okay, so let us start. This is the recap of the previous class. I told you in the yesterday class we have discussed some question on the line to ground fault and the analysis of the double line fault. The motive of this class to do some question on the line to line fault, and after that how to find out the fault current whenever the double line to ground fault occur into the power system. That means the analysis of the double line to ground fault. Okay, so let's start with the question of line to line fault. In this question we will find out the every parameter. We will find out the value of current, the phase voltages and the line voltages. A three-phase generator is rated at the 25 MV and the 13.2 kV. The MV and the kV of the generator are given. The positive sequence sub-transient reactance is 0.20. The negative sequence reactance is 0.30. And the zero sequence reactance is the 0.10. The neutral is solidly grounded. A line to line fault occur in the B phase and the C phase. What it means? Suppose I have a three line, A phase, B phase and the C phase. A, B and C. And there is a short circuit between the B phase and the C phase. The fault impedance are not given, so you will take it as a voltage fault. So B phase current and the C phase current, this is my B phase current IB and the C phase current IC. Clear? So we all know that IB is equivalent to minus IC, and this is the fault current. Fault current is nothing but IB minus IC. And yesterday I told you, whenever the line to line fault occurs, the positive sequence and the negative sequence network would be connected in parallel. So if I draw the sequence networks at the time of line to line fault, this is one angle 0 degree, then Z1, and there is a negative sequence network Z2. So this is my IA1, and opposite of this is the IA2. No zero sequence current would be flowing when line to line fault occur into the power system. So we can say that IA1 is equivalent to 0 as no negative sequence current flows when line to line fault occurs, but IA1 is equivalent to the minus IA2. IA1 is equivalent to the minus IA2. And what is the value of IA1? You can easily find out 1 angle 0 degree Z1 plus Z2. 1 angle 0 degree Z1 plus Z2. And if I multiply it by root 3, you will get the fault value of current, the fault current. Okay. Now, initially we have to find out the value of IB and the IC. As I told you, the fault current that is equivalent to the IB is nothing but minus J root 3 divided by Z1 plus Z2. So minus J root 3 divided by Z1 plus Z2, only the reactive is there. So minus J root 3 J 0.20, J 0.30, J 0.20 plus J 0.30. Now, so what you will get? The root 3 divided by 0.5 under root 3 divided by 0.5, that is the 3.464 in magnitude wise, that is 3.464 pu. Clear? Magnitude wise it is a 3.464 pu, and this is no doubt the negative current. So this is the IF. Now we have to find out the IC. So second part is the IC is nothing but the minus IB. IC and IB are the same here. So negative means the negative of this one, that is becomes the 3.464 pu. So in this way you can find out the value of IB and IC. If somebody asks you the value of IA current, because the fault is occurring into the B and C phase only, so the IA current will equivalent to the 0 only. Clear? So in this way you can find out the value of IB and IC. Now we have to find out the line voltages like VAB, VBC and VCA. We all know that the VAB is nothing but the VA minus VB, or the VBC is the VB minus VC. So first of all, we will find out the phase voltages like VA, VB and VC, and then we can find out the line voltages. To find out the phase voltages, we will use the sequence voltages and the sequence current. That means we will use the sequence network. Okay. So let's find out the sequence current and the sequence voltage. So we all know that the sequence current IA0 is the 0 because no zero sequence current flow when line to line fault occur. And here you can say the IA1 is the 1 angle 0 degree Z1 plus Z2. So IA1 is the 1 angle 0 degree Z1 plus Z2. This is the positive sequence and negative sequence. J 0.20 plus J 0.30. That means 1 upon 0.5 means 2 pu. That is the minus J 2 pu is the value of IA. 0.5 means 1 pu. Similarly, IA2 is the negative of minus IA1. So it is become J2 pu. It is minus J2, it is a plus J2 pu. So this is the value of positive sequence, negative sequence and the zero sequence current. Now let's find out the sequence voltages. How to find out the sequence voltages? See, this is my zero sequence network. It is a Z0 and the current is flowing is a IA0. and its terminal voltage is the VA0. Because no current is flowing, IA0 is equal to 0, so the VA0 is also equivalent to 0. So the VA0, that means the zero sequence voltage is equal to 0. Now, the positive sequence, if I draw the positive sequence network, it has a source and a impedance, positive sequence impedance, and its terminal voltage is a VA1. So basically, VA1 is EA, that is the one angle 0 degree, minus current flowing is a IA1 into Z1. So 1 minus IA1 is minus J2. It is a minus J2. And Z1, that means the positive sequence reactance, J0.2. J0.2. So minus minus is become plus J square 0.4, and we all know that J square is nothing but the minus 1. So 1 minus 0.4, it is become 0.6. So the positive sequence voltage is nothing but the 0.6 pu. So now we have the zero sequence voltage, the positive sequence voltage. Now find out the negative sequence voltage from the negative sequence network. So the negative sequence network will be a simple reactance of Z2 where the IA2 current is flowing. Its terminal voltage is a VA2. So VA2 is nothing but minus IA2 into Z2. Minus IA2 into Z2. Clear? Minus IA2, J2. So minus, it is a J2. And the negative sequence reactance, J0.30. J0.30. So it is become minus J square 0.6, and we all know J square is a minus 1. So it is become 0.6. Minus and minus is become plus. So VA2 is become 0.6. Any problem till now? Is everyone is clear how to find out the sequence voltages and the sequence currents? Clear? Once you know the sequence voltage and the sequence current, you can easily find out the phase voltages, because you know the relationship between the phase voltage and the sequence voltage. How? See, now put the VA. VA is nothing but the VA0 plus A square VA1 plus A into VA2. Clear? Now we know the VA0, VA1, VA2. VA0 is the 0 plus A square. The value of VA1 as well as VA2 is same as the 0.6. So it is a 0.6 plus A 0.6. If I take 0.6 as a common term, then it is become A square plus A. As we all know that 1 plus A square is equivalent to 0. That means the A plus A square is nothing but minus 1. So A plus A square is a minus 1. So it is become 0. Minus 0.6. So in term of PU, you just get the value of VA, that is the minus 0.6 PU. Clear? So this is my VA voltage in PU term. Clear? Now let's find out the VB. Let's find out the VB. VB is the VA0 plus sorry, this is my VB. This was equation for the VB. VA is directly VA0 plus VA1 plus VA2. So VA0 is the 0. It's a 0.6 and the 0.6. So VA is 1.2 pu. 1.2 pu. So VA and VB we got. Now just find out the value of VC. VC. VC is VA0 plus A into VA1 plus A square into VA2. VA0 is the 0. A 0.6 because the value of VA1 and VA2 both are equivalent to 0.6 only. Just put the value of VA1 and VA2. Again, if I take the 0.6 as a common term, it has become A plus A square. As I told you, A plus A square is nothing but the minus 1. So it has become minus 0.6 pu. Clear? Any doubt till now? How to find out the phase voltages if you know the sequence voltages and the current? Clear? See, now we will find out the value of VAB, VBC and VCA. First, I just find out the value in term of pu quantity, then I will convert into the actual quantity. So, VAB is nothing but the VA minus VB. 1.2 minus 0.6. That is the 1.8 pu. In term of pu, it is a 1.8 pu. Similarly, if you have to find out the VBC, it is VB minus VC. VB is minus 0.6. It is also minus 0.6. So minus 0.6 minus 0.6. It has become 0. The 0 pu. Then VCA is the VC minus VA. Minus 0.6 minus 1.2. That is a minus 1.8 pu. Clear? So in this way we have got the value of line voltages in term of pu. But we have to find out the actual voltages and the actual current. So let's find out the actual quantity. So to get the actual quantity, we require the base quantities first. So you can find out the base quantity from the rated one. It is a 25 MVA and the 13.2 kV. So, sorry, 25 MVA, 13.2 kV. 25 MVA, 13.2 kV. That is our base MVA. And that is the base voltage. If you know the base voltage and the base MVA, you can find out the base current. So what will be the value of base current? Always remember it is a three-phase circuit. So this is the three-phase MVA and this is a line voltage. So 25 MVA, 25 into 10 raised to the power 6 divide by root 3 into 13.2 into 10 raised to the power 3. The rated current is the base current. So 25,000 divide by 13.2 into root 3. It is 1093.46. So in this way you can find out the value of base current. Once you have the base current, then multiply the Q current with the base current, you will get the actual value of current. So you have to find out the actual value of IB and IC. IB in term of ampere, actual value. IC in term of ampere. We already got the IB and IC in term of PU, that is a 3.464. It's a negative, it's a positive. Magnitude is the same, 3.464. So IB, actual quantity, is the IB base quantity, IB PU quantity into base current. Just multiply the PU quantity with the base quantity. And here you will take the base current. So 3.464 is the base, 3.464. Minus means the B current and the C current is opposite to each other, that's all. Multiply by the base current, that is the 1093.46. 1093.46. 3.464. 3787.745 ampere. This is the actual value of B phase current. Similarly, you can say the actual value of C phase current. Instead of minus, it has in the positive 3.464. Base current is the same, 1093.46. So it has become 3787.745 ampere. Clear? So in this way you can find out the value of actual current by multiplying the base current with the PU current. Now there is a catch. If you will convert this PU voltages, line voltages, into the actual voltages, what mistake mostly student committed here, that they will take the base voltage as a line voltage, but you don't have to take the line voltage as a base voltage, because we have just got this value VA from the sequence network, and the sequence network is always the per phase network. So what you have to do, either you directly connect the VA pin PU into the actual quantity, then you will get the VAB by subtracting VB from the VA, or always take the phase voltages as a base volt only, because our sequence network is always the per phase basis, it is not the line voltages. Even if you are getting the VAB line voltages here, but always multiply it by the phase voltage of, or you can directly convert this phase voltage into the actual quantity, then you will get the VAB by subtracting VB from VM. So now this is my base voltage 13.2 kV, but it is a line voltage. So base voltage per phase. Base voltage per phase 13.2 kV, 13.2 kV divide by root 3. Seven six two one 7621.02 volt. Clear? 7621.02 volt. Now to get the actual VAB, the PU VAB we know, that is a 1.8. So 1.8 multiplied by base voltage 7621.02. Are you getting my point? Why I am taking the base voltage per phase? Because our sequence network is always a per phase network. So 1.8. So never take the line voltage as a base voltage. So it is 13717.8 volt or 13.717 kV. VBC is the 0 and VCA is the negative of this, minus 1.8 into 7621.02. So you will get the minus 13717.8. Is that clear? Is that clear? So your catch is that when you have to get the actual line voltages, even to get the actual line voltages, you have to take the base voltage as a per phase voltage only. Clear? So I took these questions so that you must know how to find out not only the fault current but the phase voltages, phase current, line voltages. So in this way you can find out the every quantity. Okay, let's take one more example. Then I will move to the line to line, double line to ground fault. A 20 MVA 6.6 kV star connected generator has a positive, negative and the zero sequence reactance 30%, 20%, 7%. A reactor with 5% reactance based on rating of generator is placed in the neutral to ground connection. A line to line fault occur at the terminal of generator when it is operating at the rated voltage. Clear? The initial symmetrical fault current will be. So either you can find out first fault current in term of Q, then multiplied by the base quantity. So for line to line fault, what is the formula to get the value of fault current? Root 3 into E. I am just talking about the magnitude, otherwise it's a minus will come. The x1 plus x2. So zero sequence reactance does not come into the picture. When the zero sequence reactance is not coming into the picture, that means this reactance is also does not come into the picture. So do not confuse why this reactance is given. The generator is grounded through this reactance, but it will not come into the picture for the line to line fault. So root 3 E is a 1 only. X1 plus X2, 30% and the 20%, it is become 0.3 plus 0.2. You have to find out only the magnitude. So root 3 divided by 0.5. 3.464. It's a magnitude PU. And negative, it's a magnitude only. 3.464 PU is a. Now, just find out the value of base current. Base current. So how to get the value of base current? It's a 20 MVA and the 6.6 kV. 20 MVA, 6.6 kV. (6.6) into under root 3. 1749.54. So you got the value of base current. Now multiply the Q quantity with the base quantity to get the actual quantity. So the actual value of fault current, is nothing but the 3.464 into 1749.54. 6060. Option is wrongly mentioned here. 6060 was the correct answer. Clear? Is the right option. So it's a very simple question, but sometimes some student get confused why this reactance is given, the neutral reactance and the why the zero sequence reactance is given. Even if the zero sequence reactance and the reactance of the neutral is given, but it does not come into the picture whenever the line to line fault occur into the power system. Only positive sequence network and the zero sequence network will come into the picture. Clear? Okay. So till now we have already been discussed. So we have discussed about the symmetrical fault, that is the three phase fault, then line to ground fault and the line to line fault. Now one more unsymmetrical fault left, that is the double line to ground fault. That means the two line is short circuited with the ground also. It may be through the fault impedance or it may be the voltage fault. So how the positive sequence, negative sequence, the zero sequence network will come into the picture, and how we can get the value of fault current in case double line to ground fault occur into the system. Let's find out. Okay. So let's do the analysis of the double line to ground fault. This is my system. Alternator, there may be transformer in the transmission line. Now the B phase and the C phase is short circuited to the ground through a fault impedance of ZF, or you can see this through this circuit. The B phase and C phase is short circuited through the ground of the ZF. So we are assuming, what was our assumption? That the no current was flowing before occurrence of the fault. No current was flowing before occurrence of the fault. That the current will start flowing only when the fault will occurs. So IA current is the zero because it is not short circuited, only the B and C phase current will be there. So what will be our equation? Our equation will be like this: IA current is the zero, IB and IC, they are the fault current. IF is the IB plus IC. The fault current is equivalent to IB plus IC. Clear? And the value of VB and VC is nothing but IB plus IC into ZF, because the current here is the IB plus IC. IB plus IC into ZF. IB plus IC into ZF. IB plus IC into ZF. Clear? Okay. Now, as we know, IA is the zero. What it means? IA 0 means the IA 0 plus IA 1 plus IA 2 is equivalent to 0. Or you can say the IA 1 plus IA 2 is become minus IA 0. Now, VB is equivalent to VC. VB and the VC are same. Or first find out VB. VB is VA0 plus A square VA1 plus A into VA2. VA0 plus A VA1 plus A square VA2. Now, this VA0 and the VA0 will be cancel out. A square minus A square minus A, VA1 is the A square minus A, VA2. Again, the A square minus A will be cancelled out. That means the VA1 is equivalent to VA2. You can, from this it is clear that the positive sequence network and the negative sequence network are connected into the parallel. That's why their voltages are equal. Clear? Now, VB is the IB plus IC into ZF. VB, third equation is the VB is the IB plus IC into ZF. This is my third equation. Clear? Now, what is the VB? VB is the VA0 plus A square VA1 plus A into VA2. This is the VB. IB is IA0 plus A square IA1 plus A into IA2. This is IB. IC is IA0 plus A into IA1 plus A square into IA2. So, IB plus IC multiply by ZF, multiplied by the ZF. Now, we know that the VA1 and the VA2 are same. So, it is become VA0 plus A square VA1 minus A into VA2, because the VA1 and VA2 are same, plus VA1. So, instead of using the VA2, I will using the VA1. Now, here IA0, it is become 2 IA0 plus A square plus A IA1 again A plus A square IA2 into ZF. Now, we all know 1 plus A square is 0. That means the A plus A square is a minus 1. So, that is the 2 IA0. It is a minus 1. So, minus IA1. It is also minus IA1 minus IA2 into ZF. 2 IA0, IA1 plus IA2 into ZF. Now, IA1 plus IA2 is a minus IA0. So, minus IA0, that means it is become 2 IA0 minus IA0 into ZF. So, this is VA0 plus A square plus A VA1, and we know A square plus A is nothing but the minus 1. So, VA1. So, VA0 minus VA1. Clear? Now, VA0 minus VA1 is equivalent to 3 IA0 ZF. 3 IA0 into ZF. So, by using all these equations, I will connect the sequence network. So, here it is clear VA1 is equal to VA2, that means the positive sequence network and the negative sequence network, they are connected in parallel. So, you can say the positive sequence network and the negative sequence network are connected in the parallel. positive sequence and the negative sequence. Positive sequence network, negative sequence network. Because its voltage is the VA1, its voltage is a VA2, and the VA1 and the VA2 are equal. So that means they are connected in parallel. Clear? This is how we can connect the PSN and the NSN. But see here, the VA0 minus VA1, that means if I draw VA0 means the zero sequence network. Zero sequence network voltage VA0. If I subtract minus 3IE0, current flowing here is a IA0. That means you will take a impedance of 3ZF. So there will be a voltage drop of 3IA0ZF. It is equivalent to VA1. It is equivalent to VA1. VA1 means that is the positive sequence network. So now combine these two. Combine these two. PSN and the NSN are connected in parallel, and between the ZSN and the PSN there is a impedance of 3ZF. So what will you get? You will get this. See, PSN and the NSN, they are connected in parallel, and between ZSN and the PSN there is a 3ZF. This point is clear? They are in parallel, and between ZSN and the PSN there is a impedance of 3ZF. Now, if I redraw the ZSN, PSN and the NSN, this is my zero sequence network. It is having only a zero sequence reactance. Positive sequence network is having a energy source and the positive sequence impedance. NSN is also having a only negative sequence impedance. Clear? So you can say the Z0 and the 3ZF, they are connected in series, and these two are connected in parallel of Z2. That means if I draw a positive sequence network E1 and Z1, E1 and Z1, if I combine these two, Z0, 3ZF are in series, and the combination of these two is connected in parallel of Z2. So there is a impedance Z equivalent. And how to find out Z equivalent? Z0 plus 3ZF in parallel of Z2. Z equivalent. Z0 plus 3ZF. Z0 is also having a neutral impedance. It is basically Z0 plus 3Zn. Always remember. And Z2 in parallel of Z2. So Z equivalent will be Z0 plus 3ZF multiply by Z2, Z0 plus 3ZF plus Z2. Always remember this thing. That this Z0 is the overall Z0. That means it is a ZG0 plus 3Zn. That means the zero sequence impedance of alternator plus 3 times of the neutral impedance. So this is combined of this. So once you got this, then you can easily find out the value of IA1. So what is the value of IA1? So value of IA1, E, that is the 1 angle 0 degree, Z1 plus Z equivalent, 1 angle 0 degree Z1 plus Z equivalent is this. Z0 plus 3ZF multiply by Z2, Z0 plus 3ZF plus Z2. Is that clear? So this is how you can find out the positive sequence current. See, in double line to ground fault, all the three sequences come into the picture: positive sequence, negative sequence, and the zero sequence. Once you got the positive sequence current, by using this you can find out the negative sequence current and the zero sequence current. How? See, for simplicity, if I draw this circuit, it is like this. I have a positive sequence network. It is connected in parallel of negative sequence network Z2, and between these two there is impedance of 3ZF. Between positive sequence and negative sequence, sorry, zero sequence network, there is a 3ZF. Clear? So I got this current IA1. This is IA1, the current output from the positive sequence network. This is IA2, current output from the negative sequence network, and this is IA0, current output from the zero sequence network. If you know this IA1 by using the current division rule, this current is coming here, it will divide into the two parts, either this and this. You can find out the value of IA2 and IA1. So from current division rule, see, IA2 is a negative of this current, and this current is what? This current is nothing but the IA1 impedance of this branch, Z0 plus 3ZF, sum of all these, Z2 plus Z0 plus 3ZF. IA0, it is also negative of this current, and this current is, by using current division rule, the IA1 will be divided into two parts. This is the impedance of this Z2, negative of this, because this and this is the opposite to each other. Z2 plus Z0 plus 3ZF. Clear? In this way you can find out the positive sequence, negative sequence, and the zero sequence current. What is our main motto? Our main motto to find out the value of fault current. So how you will get the value of fault current? Once you know this, the fault current is the IB plus IC. What I told you, the value of fault current is nothing but the sum of IB plus IC. Sum of IB plus IC. And IB is the IA0 plus A square IA1 plus A into IA2. IC is IA0 plus A into IA1 plus A square into IA2. Clear? Now IA0, it is become 2IA0. IA1, if I take IA1 common, it has become A square plus A. A square plus A IA1. If I take IA2 as a common term, A plus A square IA2. Now A plus A square is nothing but the minus 1. So 2IA0 minus IA1 minus IA2. 2IA0 IA1 plus IA2. And I told you IA1 plus IA2. What was that? it is minus Ia0. It is minus Ia0. So minus Ia0 3 Ia0. So 3 times of Ia0 is the value of fault current. In this way, you can easily find out the value of fault current. Clear? If you know the sequence current, you can find out the sequence voltages, and from the sequence voltages, you will easily find out the phase voltages and the line voltages. Is that clear? Is that clear? Suppose if somebody asks you to find out the phase voltages, how you will get the phase voltages? See, VA1 is a EA minus IA1 into Z1. This is 1 angle 0 degree, IA1 we know. Similarly, the VA2 is minus IA2 into Z2. We already got the value of IA2 multiplied by the negative sequence impedance, and the VA0 is minus IA0 into Z0. Z0 means it is including the Zn. Clear? If you know the VA1, VA2, VA3, you will easily find out the value of VA, VB and VC. VA is the VA0 plus VA1 plus VA2. Similarly, you can get the value of VB, which is the VA0 plus A square VA1 plus A into VA2. And the VC is the VA0 plus A VA1 plus A square VA2. Once you got the phase voltages, you will easily get the, once you get the sequence voltages, you will get the phase voltages. And from the phase voltages, you will find out the line volt also. Like if you have to find out the VAB, it is the VA minus VB. Similarly, the VBC will be VB minus VC. VC is a VC minus VA. Clear? So this is all about how to get the fault current, the phase current, the phase voltages and the line voltages if the double line to ground fault occur into the system. So now we will conclude here. Whenever the three phase fault occur, only the positive sequence component come into the picture. For line to ground fault, all network come into the picture. For line to line fault, only positive sequence and the negative sequence component come into the picture, and the double line to ground fault, all three sequence network come into the picture. So here I am concluding. I will do some question for the line to ground fault in tomorrow class. So let me conclude in the 2 minutes what we have discussed in today class. We have discussed some one question based on the line to ground fault, line to line fault, Here we have learned that how to get the value of fault current, phase current and the line voltages and the phase voltages. Then we have also done the analysis of power system when double line to ground fault occur into the system. We have learned how to get the fault current, phase voltages and the line voltages whenever the double line to ground fault occur into the system. Okay, this is information for you. Unity is basically a software through which you can get the interactive poll during the YouTube class. It is also having a 3D model library. YouTube notification is also there. Unity.com. You can ask the doubt also. You will get the dashboard and the leaderboard whenever we conduct the poll. After the complete class, you will get what is your ranking through the dashboard and the leaderboard. You will also get the live class notes and the doubt. You always get the PDF of this class that we conduct into the YouTube. And you can also do the video call. The video call is also possible into the YouTube classes. So these are some new features of the Unity software that is only for the YouTube classes. See, this is how you will participate into the poll. You have to just write A, B, C or D, the correct option A, B, C or D in the chat box. Whenever you will write the correct option A, B, C and D, you will able to participate into the poll. And similarly, you can also ask the doubt in the YouTube classes. So the tomorrow will be our last classes. In the tomorrow classes, I will discuss some question based on the double line to ground fault. In addition to double line to ground fault, I will also do some more question for the different type of faults that occur into the power system. Clear? So thank you everybody.